Hello everyone, it's an honor to give a talk at the virtual workshop on Ricci and scalar curvature. It's in honor of Misha Gromov, and thanks the organizer for the invitation. So today we're going to talk about the asymptotic convergence for modified scalar curvature flow. This talk contains four main part. So in the first part, we're going to talk about the background, and we're just gonna introduce different type of curvature flow. And then we're going to talk about some known results, which also the motivation of this work. And in the third and the fourth part, we're going to talk about our main results and the idea of the proof. Okay, first let's look at the most well-known flow. I mean, one of the most well-known flow, which is mean curvature flow. So if we start from initial surface M0, and this initial surface is compact, mean convex. Mean convex meaning that the mean curvature is greater than 0, and it's an n-dimensional hypersurface. So we consider the following flow equation, which is xt equals minus h times nu. Here, x is the position vector, and the nu is the outward normal direction to the surface M0. So Huisken in 1984 showed that if our initial surface M0 is convex, so instead of having mean, instead of being mean convex, which is mean curvature is greater than 0, in this paper, Huisken required that every principal curvature is greater than 0. So M0 is convex. Then this flow will converge to a single point P in finite time. And if we rescale this flow, we'll see that this rescaled flow converges to a sphere Sn. When we say rescaling, we mean like rescale the flow in space-time. So basically it means that around the point P, we zoom in into this flow, we can see that this flow become more and more circular. Okay, before we start to talk about other type of flow, I want to give you some definition. First, we're going to define what is the sigma k curvature of a hypersurface M. So the sigma k curvature is defined as following. So sigma k equals the sum of kappa I1 times up until kappa ik, where kappa of M are the principal curvatures of the manifold M. And we say hypersurface M is K convex if the principal curvatures of M at any point of M satisfies that the principal curvatures belongs to a gamma K cone, and the definition of gamma K guarding cone is following. So we can look at some example. When we actually we can easily see that in this case sigma 1 is our mean curvature, which is the sum of kappa I, and sigma n is Gauss curvature, which is the multiplication of kappa I. And sigma 2 is our scalar curvature. Okay, let's go back to the guarding quant part. So we can see that one convex. One convex means that sigma 1 is greater than 0. So one convex is equivalent to mean convex. And unconvex means that the Gauss curvature is greater than 0, and the sigma n minus 1 curvature is greater than 0, and up until mean curvature is greater than 0. So we can see that actually unconvex is convex. Okay, so when we say two convex, we mean that the scalar curvature is positive and the mean curvature is positive. So let's look at a very standard fully nonlinear curvature flow, which is the Gauss curvature flow. So flow generated by the Gauss curvature was first started by Frey in 1974. The purpose of it is to model the shape change of tumbling stones. In general, people consider the alpha power of the Gauss curvature flow, which is the equation is xt equals minus sigma n to the alpha times 2, and here alpha is greater than 0. There's a very well-known conjecture. It says that for alpha greater than 1 over n plus 2, the flow deforms a convex hypersurface M in Rn plus 1 into a round point. So which means that as long as the power is greater than 1 over n plus 2, if we start from a convex hypersurface M, convex compact, it's going to disappear at one point. And if we rescale this around this point, we can see that the flow become more and more sphere. So why we require alpha greater than 1 over n plus 2, actually the power matters. So when alpha equals 1 over n plus 2, it was proved by Ben Andrews that actually a convex hypersurface M going to deforms into a ellipse, which means that if alpha equals 1 over n plus 2, you zoom in around the singular point, what you can see is a ellipse instead of round sphere. The round sphere is a type of ellipse, but just saying that it can disappear like as an ellipse. And when alpha less than 1 over n plus 2, nothing is known so far. So anyway, this conjecture is about alpha greater than 1 over n plus 2, and it took several decades for people to completely solve this conjecture. So initially, Cho in 1985 confirmed this conjecture for alpha equals 1 over n. So when alpha equals 1 over n, the equation becomes xt equals minus sigma n to the 1 over n times nu. And this is a relatively special case because sigma n to the 1 over n is homogeneous of degree 1, and also it's concave. So this is functional, it's a concave functional with homogeneous degree 1. Okay, later in 1999, Andrews confirmed this conjecture for alpha equals 1 and n equals 2. So Andrews was able to prove this conjecture only for two-dimensional manifold. And in 2017, Guang and Ni partly confirmed this conjecture for alpha equals 1 and any dimension n. Why we say it's partly confirmed this conjecture, because they didn't show that this flow disappear as a sphere. What they show is if you zoom in around the singularity, what you get for the in the limit is a surface that satisfies sigma n equals x dot nu, but they didn't prove that a convex compact manifold satisfies this equation is a sphere. They only know that the limit surface hypersurface satisfies this equation. So Andrew Guan Ni proved in 2016 that partly confirmed this conjecture for alpha greater than 1 over n plus 2 for any dimension n. So here they proved the same thing. They proved that the limit hypersurface satisfies sigma n to the alpha equals x dot nu. But again, they didn't show that this hypersurface is in fact a sphere. In 2017, Brandel, Choi, and Daskalopoulos complete the proof of this conjecture. So they proved that when alpha greater than 1 over n plus 2, convex compact hypersurface satisfy this equation. So when alpha greater than 1 over n plus 2, they proved that they all sphere. So then this conjecture is completely conformed. So next we're going to talk about some applications of general curvature flow. So typical applications of general curvature flow, including you can use it to prove inequality, just like Huisken and Immen's famous work of Penrose inequality. That was the inverse mean curvature. That was proved by using inverse mean curvature flow. And also, one can use the general curvature flow to prove the existence of prescribed curvature hypersurface. For example, you can use the general flow method to construct different type of constant mean curvature hypersurface. So here, the example we're going to talk about is to use the general curvature flow to prove core mass integrals. As parametric inequality for core mass integrals. So in 1990, Jehart and Erbers considered the following curvature flow, which is xt equals sigma k minus 1 over sigma k times nu. And we can see that when k equals 1, it's just the inverse mean curvature flow, where nu is the outward normal. So they showed that if the initial surface is k convex, star-shaped, as we mentioned before, k convex means that the sigma k curvature is greater than 0, and the sigma k minus 1 curvature is also greater than 0, and up until sigma 1 curvature is greater than 0. So, and also the initial surface need to be star-shaped, means that x dot nu is greater than 0 everywhere. X is the position vector and nu is the normal. So if the initial surface satisfies these two conditions, then they proved that the flow exists for all time t greater than 0, and after rescaling, it converges to a round sphere. So, and then using this result, Guan Li in 2009 proved the parametric inequality for non-convex star-shaped domains. So, what is the parametric inequality? So, we let v n plus v sub n plus 1 minus k equals this constant times the integral of sigma k minus 1 curvature over the manifold. So we can see that when k equals 1, we n of omega just equals a constant times the area of boundary of omega. And we define ik of omega as the quotient of Vn plus 1 minus k. So, and Guan Li considered the reparameterization of the flow equation 1, which is xt equals sigma k minus 1 over sigma k minus r of t times nu. Here, r of t is a quality only depends on time. So by a brilliant choice of this quality, they showed that the quality I sub k of omega is increasing under the flow 2, and by Jihad and Erber's earlier result, we already know that in the limit, in the limit of this flow 2, it's a round sphere. So we know that this flow 2 flow convex set omega into a ball, and because this quality I sub k increase under this flow, that means that I sub k of omega is always less than or equal to I sub k of b. So this generalized the Alexandrov-Fincher mass integral inequality, and the original inequality was proved by Alexandrov in 1930s. What he proved is only true when omega is convex. So here he proved that when omega is convex. So that's but Guan Li proved for omega is k convex and star shaped. Okay, so this is the first example of application of general curvature flow, and next we're going to talk about some other application of general curvature flow, which is also the motivation of this work. So basically the flow we study is to construct solutions for the dual Minkowski problem. Actually, the flow we are doing is more general than that, but it starts with the dual Minkowski problem. So we're going to first talk about what is the dual Minkowski problem. So this problem was introduced by Huang, Ludwig, Yang, and Zhang in 2016. So the question is, given a finite Borel measure mu on the sphere and a real number q, what is the necessary and sufficient conditions on mu so that there exists a convex body K which containing the origin in its interior, such that this Borel measure mu equals the Q's dual curvature measure C tilde sub Q of K. So what is the Q's dual curvature measure? So we denote M as the boundary of omega. So okay, so suppose this is our M, and here is our sphere Sn, and the omega here actually is a set on Sn, but here for make it easier, we just say that omega is 1 point on Sn. So say omega is, if omega is a point, which we say that it's the North Pole. Okay, then what is chi? Chi is this point. I mean, it's this direction. So this direction is our chi, because in this direction, this is our radial direction. I mean, this is our radial function r of chi. So this point is r of chi times chi. Chi is the direction. R of chi is the radial function. And at this point, the normal direction is omega. So therefore, A star of omega, when omega is the North Pole, actually is this point. Okay, then the Q's dual curvature measure is defined by this integration. So one can derive that the dual Minkowski problem is equivalent to the solvability of the following equation, which is u of x over r to the alpha of chi times k of p equals f of x. So here p is a point on the manifold M, and the nu of p is our x. So chi is the direction of the point p, right? So back to our example. So okay, this is not circular. So this is our Sn, and then this is M, and so and then this is our point P. So then this direction is our chi, and this direction is our x, which is the normal direction at the point P. So, and u of x is the support function of the manifold M. alpha equals n plus 1 minus q. So essentially, the Dual-Minkowski problem is to ask the necessary and sufficient condition on the function f of x such that equation 3 is solvable. So Huang, Ludwig, and Yang and Zhang in 2016 proved the existence of symmetric weak solutions to equation 3 for the case when q belongs to 0 to n plus 1 and some other conditions. So first condition that is easy to see that they need some kind of symmetry on the function f of x. Okay, so, and later Li Sheng Wang started this problem using modified Gauss curvature flow. So what they did was to consider the modified Gauss curvature flow looks like this, which is the xt equals minus f of nu times r to the alpha times k times nu, where k is the Gauss curvature of the hypersurface m sub t, and x is the position vector, nu is the unit outer normal at the point x, f is a given positive smooth function on Sn, and r is the distance from the point x to the origin. In other words, r is the radial function. So we can rescale the equation 4 to obtain the following normalized flow equation 5. So essentially it's the equation 4 plus a position vector. So Li Sheng Wang proved that if we start from a smooth, closed, uniformly convex hypersurface in Rn plus 1, so uniformly convex here, they mean that every principal curvature is strictly greater than 0. And also, this initial hypersurface contains the origin in its interior. So f is a positive smooth function on Sn. If our alpha is greater than n plus 1, then the flow 4 has a unique smooth solution mt for all time t greater than 0. And if we rescale this hypersurface, so when t goes to infinity, we rescale the flow in space-time, the rescaled hypersurface converges smoothly to the unique smooth solution of this equation 3. So what they have proved here is if q less than 0, then for a very large class of function f, the equation 3 is always solvable. Okay, analogously, we can ask following question. So if given a measure d mu equals f d sigma Sn, so which means we give a measure on Sn with positive function, f is a smooth function on Sn, does there exist a convex body omega such that the following measure equals mu? Here this measure f sub kq defined as the following. So we can consider it as a dual LQ Christoffel-Minkowski problem. So this functional, I mean this measure f can be interpreted as a dual case Q area measure. So this is equivalent to solving the following equation. Here has one more f. So this is equivalent to solving the following equation, which is r to the n plus 1 minus q times the sigma k curvature of the boundary of omega equals u over f of x. Here u is still the support function of m, and f is the given function. So this is actually the principal curvature of boundary of omega. Okay. So lesion 1 considered the following flow problem, which is xt equals minus r alpha times sigma k times nu. So here, actually, this is equivalent to say that our function f equals 1. So they didn't start the general function f, only f equals 1. So what they proved is, if we start from a smooth, closed, and uniformly convex hypersurface, which encloses the origin, if alpha is greater than or equal to k plus 1, the flow 6 has a unique, smooth, and uniformly convex solution MT, which converges to the origin. After proper rescaling, the rescaled surface m tilde t converges exponentially to a sphere centered at the origin in the C infinity topology. So they proved this. And they also proved when k equals 1, so it's the special case. So essentially it's a case that xt equals minus r alpha times mean curvature times nu. So in this case, they proved that we only need to start with a weakly mean convex hypersurface. So the initial surface only need to satisfy that h is greater than or equal to 0. Suppose that the initial surface also is star-shaped with respect to the origin, and alpha is greater than or equal to 2, then the equation 6 has a unique smooth solution MT for all time t greater than 0, and if we rescale this flow, we know that the limit is a sphere. So alpha, they also proved that alpha is greater than or equal to 2 is optimal, because they proved that when alpha less than 2, they constructed a counterexample that the flow doesn't converge to the origin, and also there's the rescaling of the flow is not a sphere. So one may ask that why they only start the f is constant. So the goal is to start the for any function f, but because this is sigma k curvature, there's a technical difficulty. We will mention more later. But to start the f is any say positive or smooth function, and then if we can prove say a similar result as they proved in the James paper for Gauss curvature, that would be a very interesting result. Okay, so this is the part 1 of this talk.